A-Level Chemistry Paper 1, Specimen version 0.5. Let's have a look at this first of all. So before we start question number 1, let's have a look at different shapes of molecules. Let's go with no bonding pairs at all. Let's discuss no lone pairs at all bonding pairs. So 2 bonding pairs, no lone pairs, something like BeCl2. Beryllium's in group 2, 2 electrons, it's outer shell. Cl's in group 7, wants to gain 1, so you have BeCl2. No lone pairs because beryllium's in group 2, 2 electrons, outer shell. Both those are used in bonding pairs, and so it's a bond angle of 180, it's linear. Let's have a look at the next one where there's no lone pairs, but with 3 bonding pairs. 3 bonding pairs, something like BCl3 or BF3, where boron's in group 3, 3 electrons, outer shell. Bonds 3 Fs, an F, an F, and an F, and so no lone pairs left over. All 3 electrons in the outer shell are involved in bonding pairs. Stays planar, so as long as these 2 numbers add up to 3 or less, it's going to stay planar. There are some slight exceptions to that rule that we'll see in a minute, but broadly, as long as these 2 numbers, the number of bonding pairs and the number of lone pairs, is 3 or less, then it stays planar. So it's trigonal planar, 3 in a flat shape, planar shape, bond angle 120. Let's have a look at the next one where there's bonding pairs and no lone pairs. So 4 bonding pairs, 4 add 0 is 4, so that's larger than 3, so it's no longer flat, it's no longer planar, and it can go into a tetrahedral shape to give a bond angle of 109.5. Remember that 109.5 because that's going to come in useful when we consider what happens when we introduce lone pairs. So let's have a look at 5 then. 5, so what actually happens is on 5, so 5 bonding pairs, so something like PCl5, this by the way was methane, something like that. PCl5, you get the trigonal planar shape, but you also get 1 up and 1 down, so the first 2 bonding pairs go as far away as they can do, and then the others go at 120 each, so you get a bond angle of 120, and then you get a bond angle of 90 between the 2 bonding pairs that are up and down from the planar shape. 6 is octahedral, so 6 ends up with sort of square planar shape with an up and a down, so that's octahedral because it would have 8 faces if all of these were joined up, so that's octahedral. 6 bonding pairs, no lone pairs. Now let's have a look what happens. We'll ignore this one for a minute. Let's have a look what happens now if we end up with a 4 shape, a tetrahedral, but we introduce 1 lone pair. So 3 add 1 is 4, so it's not going to be flat. But what actually happens is one of those bonding pairs is replaced by a lone pair here. Now we need the 4 in to consider the shape, but we can't actually see a lone pair, so you just see the shapes of the atoms. So it's pyramidal. It's got 3, 1 in the middle, and then 3. So that could be something like ammonia. Nitrogen's in group 5, so 3 bonding pairs, and then the 4th and 5th electrons are as a lone pair. And if you remember, every time a tetrahedral shape, so 4 bonding pairs, one of the bonding pairs becomes a lone pair, you subtract 2.5, so 109 take away 2.5 is 107. And the same thing works here for something like water, H2O, where you've got O in group 6, so 6 in its outer shell. 2 of them are involved in bonding pairs, and then there's 4 left over for 2 lone pairs. So if you take the tetrahedral shape and replace 2 of the bonding pairs with lone pairs, you actually only see the atoms. You don't see these these lone pairs here. You only see the atoms, and because there's 1, 2 bonding pairs replaced by 2 lone pairs, you subtract 109.5, take away 2.5, and take away 2.5 again for each of the lone pairs, and it comes out as 104.5, and that's V-shaped or bent. They've called it non-linear here, but V-shaped or bent is something easier to remember. And then there's other ones as well here, something like xenon tetrafluoride XeF4. Here we've got xenon with 8, so 4 bonding pairs, and then 4 electrons left over, so 2 lone pairs, and they do similar to an octahedral. These 2 repel the most, so lone pair repel the most, followed by lone pair, bonding pair, followed by bonding pair, bonding pair in the electron pair repulsion theory. And so these 2 repel as far away as they can, up and down, and then they leave a square planar shape. So that's the only real example of where you end up with a planar shape. 4 add 2 is obviously larger than larger than 3, so you would expect it not to be linear, but in this case it's linear because, you'd expect it not to be planar, but in this case it is planar because the two lone pairs push the 4 bonding pairs into a planar shape, bond angle 90. And then you can get other ones as well, so non-linear, so something with, say for example, 4 electrons in its outer shell bonding to 2 other atoms, then we'd end up with this kind of shape. And in that case, you would have something like trigonal planar, but one of the bonding pairs is replaced by a lone pair, and so instead of 120, you subtract 2.5, and it comes out as 117.5, and that's called V-shaped again, or bent. Let's have a look at the actual question then now. Explain how the electron pair repulsion theory can be used to deduce the shape of the bond angle in PF3. So you've got 5 electrons, phosphorus is in group 5, so there's 5 electrons in the outer shell, 3 involved in bonding pairs, 5 take away the 3 that are involved in bonding pairs is 2, so there's a lone pair and 3 bonding pairs. So there's 1 lone pair and 3 bonding pairs. So we've got something like this. We've got pyramidal, so it's like a tetrahedral shape, but one of the bonding pairs is replaced by a lone pair, so you don't see that, so you only see the pyramidal shape. Tetrahedral in 109.5, take away 2.5 is 107. So 3 bonding pairs with 3 F atoms, 1 non-bonding pair or 1 lone pair. Electron pairs repel as far as possible. Lone pair repels more than bonding pairs. So you just got to name the, just got to quote the electron pair repulsion theory here. That electron pairs or lone pairs repel as far as possible, and then you can just say lone pair repels more than bonding pairs, or lone pair repels more than lone pair bonding pairs, and bonding pairs repel the least. So just give a little quotation of the electron pair repulsion theory, and then you can explain the shape and the bond angle. State the full electron configuration of a cobalt-2 ion. Well, cobalt's got an atomic number of 27, so it's got 27 electrons. 2 means cobalt-2 means the cobalt's in oxidation state, plus 2, it's lost 2 electrons, so it's got 25 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 3d7 adds up to 25. Suggest one reason why the electron pair repulsion theory cannot be used to predict the shape of the COCl4 ion. Well, you predict that it's actually tetrahedral because it's got a coordination number of 4. It's got 4 ligands, 4 Cls. So you actually predict it's tetrahedral. However, with transition metals, once you introduce electrons in the d orbital, there's too many electrons in the d orbital, so transition metals have got d orbitals, and yet there's too many electrons in the d orbital really for the electron pair repulsion theory to work. So all you need to say is too many electrons in the d orbital. That means the electron repulsion theory can't be used to predict the shape. Although, as I say, you'd probably predict it was tetrahedral. Predict the shape and the bond angle in the complex rhodium ReCl4. So if we're going to predict something, if we're forced into making a prediction, then Cl4 has got a coordination number of 4, and therefore you go with tetrahedral bond angle 109.5.